Right, hello. We're taking a look at chapter 3.6, the chain rule. All right, so we have an idea of how to do derivatives. All right, we have our product rule, we have our quotient rule, our power rule. We can do some basic derivatives, do derivatives of sines and cosines and tangents. So we have the basics down. All right. But the problem that we run into is that those only work for kind of the good, nice functions. All right. The good, nice ones. What happens when there's just a little bit more going on? Okay. So for instance, we have f of x is equal to this square root function. We know how to do the derivative of a square root function. But there's more than just an x inside of that square root function. There's a 3x squared plus 1. So when you have these composite functions, a function inside of a function, we have to do this thing called the chain rule. All right. Well, before we can do that, really truly what we should do is the limit definition of this derivative. Okay, so let's do the limit as h approaches 0 of this thing. Well, to do this derivative, all right, to do this limit, we should multiply by its conjugate. Okay, so we multiply by the square root of 3x plus h squared plus 1. We change this minus to a plus, and then 3x squared plus 1. And we do the same thing on the top and the bottom. All right, so we multiply by the conjugate. What we have learned is that by multiplying by the conjugate, the square root times the square root should just cancel out. So we've got 3x plus h squared plus 1. The minus will stay, but like this times this, and then the negative times this. The middle terms will cancel. And then the square root of 3x squared plus 1 times the square root of 3x squared plus 1 is just 3x squared plus 1. But we have the whole denominator still on the bottom. We have an h, and then the whole denominator still on the bottom. Right, the top, we've got some work to do. First thing I kind of notice is that this plus 1 and this minus a plus 1, those will cancel. All right, so that makes that a little bit easier. But this 3 times x plus h squared, I do have to kind of distribute that. All right, so x plus h squared is going to be x squared plus 2xh plus h squared. And we have to multiply it by 3. All right, our x squared and 3x squared, those will cancel. That's great. Now, do you notice how everything on the top has an h? All right, so that's good because I have this h on the outside. So this h will cancel with that h, and it'll reduce that squared to now just a regular h. All right, so we have a limit. As h approaches 0 of 6x plus 3h over all right, great. So now, since there is no longer just that random h on the bottom, we can now plug in 0 for our h. We can direct evaluate now. By putting 0 in here on the top, 6x plus 3 times 0, that's just 6x. Down here on the bottom, by putting 0 here, I mean, that's fine. We still just have x plus 0. That's just x squared. So we have 3x squared plus 1. And here we have 3x squared plus 1, both inside square roots. So that is 2, and then square root of 3x squared plus 1. All right, so that is the derivative of this terrible looking function. Okay. So we can do it. It definitely takes a lot of work to be able to do a function inside of a function and to be able to do the derivative using the limit definition. But when I look at this, I start to recognize a couple things. Now, first off, the derivative of just a square root, we have learned that's like x to the 1/2 power. So that derivative is 1/2 x to the negative 1/2, aka 1 over 2 square root of x. So what I see here is that I have the 2 and the square root of my thing. So this part stayed the same. It just became a 2 on the bottom. Now on the top, instead of a 1, I have a 6x. Take a look at the thing that's inside. What is the derivative of this thing? What's the derivative of 3x squared plus 1? Well, that derivative is 2 times 3, that's 6, reduced by a power of 1, and the derivative of that 1 is gone, it's a constant. So its derivative is 6x. So you see we have its derivative here, and this thing here, we have kind of both pieces. So it's kind of like the derivative of the big function, and then also the derivative of the inside function. Okay, so it's like we do both derivatives. That is the exact chain rule. Okay, so when you have a composite function, you take the derivative of the outside function just like you normally would. All right, but then you multiply by the derivative of the inside function. Okay, so you take the derivative of the outside, leave the inside stuff just exactly where it is, and then multiply by the derivative of the inside. All right, so to do this with this function. Now, it's a square root function. So let's say it was 3x squared plus 1 to the 1/2 power. All right, so I have something inside of a 1/2 power function. To do this derivative, since there's stuff inside of our square root, stuff inside our 1/2 power, we have to do the chain rule. The chain rule says, act like this thing is just, a regular x. The derivative of a 1/2 power is 1/2, and then you take one away, so negative 1/2. The stuff that's inside just stays inside. All right, but since it is more than just an x inside of that 1/2 power, we have to then chain on, multiply by the derivative of the inside stuff. The derivative of this inside stuff, 3 times 2 is 6x, and the derivative of 1 is 0. So we just have the 6x. So this 1 over 2, 3x squared plus 1 to the 1/2 times 6x. And if we want to, we'd move that 6x up to the top. And change that 1/2 power back to a square root. Now, if we want to, we can reduce the 6 and the 2, of course, that's totally fine. So the 6 and the 2 would reduce to a 3 and a 1. We wouldn't really need the 1. All right, so you can reduce it, that's fine. I did not reduce it here because I wanted to show you that, the chain rule aspect and see those two pieces. Right, but that is the general idea of the chain rule. When you have more than just an x inside of your big picture function, the big picture here is it's a square root, but there's more than just an x in there. You take the derivative of the function just like you normally would, all right? Leave whatever's inside of it, but then chain on, multiply by the derivative of the inside stuff. All right, so we're going to practice that a few times. Next example, I see we have a function. It's a sine function. Okay, that's great. But there's stuff inside of my sine function. All right, and then I have this plus 5, a constant up here. So to do my derivative, all right, the 4 is in front of sine. All right, so I still have 4 times. The derivative of a sine function is a cosine function. All right, now there's stuff inside of here, so we just leave it. Right? But when there is stuff inside, you have to chain on, you have to multiply by the derivative of the inside stuff. All right, so there's multiple pieces here, so we're going to have a parenthesis. The derivative of this inside stuff, it's a polynomial, so a power rule. 2 times 5 is 10x to the first and then plus 3, no x's, and then the 1 will be gone. The derivative of this plus 5 is gone. It would be like a 0, so plus 0, which we don't need. Last but not least, we could maybe just make this look a little bit better. We could maybe do this 4 times this stuff. We could distribute that. So we could say 40x plus 12, and then cosine of 5x squared plus 3x plus 1. All right, so we have the derivative of our sine function is cosine. All right, the inside stuff stays. You then chain on, you multiply by the derivative of the inside stuff is 10x plus 3. All right, and then you combine what you can. This 4 and this 10x plus 3 we can multiply. All right, and that is our chain rule. All right, so a couple more examples. Next up, we have h of x is this. So to do the derivative h prime, well, this stuff is inside of a 9th power. All right, so it's a power rule. The 9 comes down in front, and we reduce by 1. The stuff inside just stays. All right, but since the stuff inside is more than just an x value, we chain on, we multiply by its derivative. The derivative of 4x to the 5th, 5 times 4 is 20x to the 4th, reduced by 1. And the derivative of a minus 5 would be 0. There's no variable there. So we can close that parenthesis. We could then maybe try to combine this 9 and this 20 can multiply together. So we have what? 180x to the 4th. I'm going to move this to the front. And then 4x to the 5th minus 5 to the 8th. All right, so that would be our derivative. We have the power rule. The 9 came to the front, reduced by 1, leave the inside. But then chain on, multiply by the derivative of the inside. And we've got that 20x to the 4th. We combined, we got our 180x to the 4th. All right, so that's the basic idea. That's our chain rule. Now, where this can just get tough is we can now start to include our chain rule with products or with quotients. Okay, so for this example here, I'm doing the derivative of f of x, that is this product. Okay, so we have to do the product rule. All right, the product rule said take the derivative of the first thing. Well, the first thing is something inside of a power, so it would be 3, and then 3x plus 1, and that would be to the second power. All right, move the 3 in front, reduce by 1. But then we have to chain on the derivative of the inside, derivative of 3x plus 1. That's just a power rule. That would be a 3. All right, so product rule says derivative of the first thing times the second thing left alone plus the derivative of the second thing. So 2 moves to the front, and we reduce by 1, so to the first power, times the derivative of the inside stuff, the chain rule. So 4x minus 5, that derivative is just 4. So the product rule says the derivative of the second thing, that's the derivative of the second thing, times the first thing left alone. All right, so that is our derivative. We can make this look a little bit better. This 3, that 3 can make a 9. This 2, this 4 can make an 8. And we've got ourselves an answer. We might be able to, simplify this a little bit. I don't think we really need to, but we could. We have some common factors in both pieces. So you might be able to, factor out some common pieces. Truly, I don't think you need to. The derivative of something that is a product is usually going to look pretty large. Now, since these are raised to power still, all but this one, I don't think we really want to distribute any of this. I don't think that we really want to multiply this out. I think we are just kind of left with this derivative of a product is still a product, and two pieces of a product. Okay, so I would leave that just like that. All right, the next one, g of x, we have a quotient. Okay, so we have to do the quotient rule. All right, the quotient rule says take the derivative of the top. So the derivative of sine is cosine. And we leave the stuff inside. But since the stuff inside is more than just an x, we have to chain on, multiply by the derivative of that bottom. So times 3. Quotient rule says derivative of the top times the bottom left alone minus the derivative of the bottom. So it's a power rule. 2 times our stuff to the first power, reduced by 1. But since the stuff is more than just an x, we have to do the chain rule. So derivative of the bottom would be 2, 5x minus 4, but times the inside stuff, derivative. Derivative of 5x is just 5, derivative of 4 is gone. So derivative of the bottom times the top left alone, all over the bottom squared. All right, so let's see if we can simplify this at all. Now, a squared would become a fourth. So I hope we're okay with that. All right, do I see anything that can really combine? Well, everything has a 5x to the fourth. Let's say 1 of them here, 2 of them there, 4 of them there. So I think I can reduce this 5x to the fourth. So that will go away. This will come down to a third, and this will come down to a first. Okay. From there, let's say we're just kind of going to collect some terms. Maybe I can distribute this since it's not squared anymore. So we've got 15x minus 12 times cosine of 3x plus 1 minus this 2, this 5 would make a 10 sine of 3x plus 1. And then 5x minus 4 cubed. I don't think that we can really reduce that much more. I think that is just where that one will have to stay. Derivative of something that's a big quotient still gives you a big quotient. Okay. All right. Next up, we have sine squared of x. Remember, sine squared means sine of x squared. Okay. So we have a sine inside of a squared function. Okay. Which means when we take our derivative, we first do the power rule. 2 to the front, inside stays, and reduced by 1, times the derivative of the inside for our chain rule. Derivative of sine is cosine. So this would be 2 sine x cosine x. All right, the derivative of cosine to the fourth which could be written like this, cosine of x to the fourth power. So the derivative is a power rule, 4 to the front, and reduced by 1, times the derivative of the inside, which is negative sine of x. Now, since this doesn't have a power, usually we would put that in front with our negative times 4 sine of x. And cosine cubed. All right, so hopefully we are feeling good about the chain rule. Now, where it can get tough is when you have something like this. All right, we have sine to the fourth power, so I'm going to have to do a chain rule to do our derivative, but there's stuff inside of our sine even. Okay, so we would think of this as like sine of 3x plus 1 to the fourth power. All right, so our derivative, g prime. First off, we have to do our power rule. The 4 to the front and reduced by 1 times the derivative of the inside stuff. Well, the derivative of a sine is a cosine. And the 3x plus 1 stays, because that's what's inside of it. But since the stuff inside of it is more than just an x, we have to do its derivative as well, a chain rule of a chain rule. So the derivative of 3x plus 1 is 3. All right, so our total derivative I see on the outside, a 3 and a 4, that will be a 12. This cube can kind of go on the side. And there we go. We've got 12 sine cubed 3x plus 1 times cosine of 3x plus 1. I guess, going back to that last problem, I move this sine to the front. And I said it's because it's not to a power. But really, I guess looking at that one, cosine's not to a power. Maybe I just like to put sine first usually. Maybe that just might be how my brain operates. Sine first, cosine second. Don't ask me why. All right, the next one, h of x is this. Well, it looks like I have a square root function with a sine inside of it and a 3x squared inside of that. So to do my derivative, I'm going to have to do a power rule. Well, I always want to rewrite the square root as the 1/2 power. So I do this derivative. Power rule times the derivative of the inside, the derivative of sine of 3x squared. Well, the derivative of sine is cosine. But since there's more inside of this than just nets, I have to do this derivative as well. 3 times 2, that's 6x. All right, so putting this all together, this negative exponent is going to go to the bottom. This 2 and this 6 are going to reduce and make a 3x. And then cosine x is also up there. Just cosine that's cosine of 3x squared. And on the bottom, I'm going to have a square root, that negative 1/2 power, sine of 3x squared. All right, so multiple chain rules can be done all at once. All right, and we just kind of have to keep taking derivatives. Last but not least, you might see some slightly different notations as you're doing the math with mass or looking through the book. And we have the Leibniz notation. Right, so I don't know how much you've read about kind of the history of calculus. There were two people who kind of co-founded calculus. Isaac Newton gets most of the credit. His math, quote-unquote math, was a little bit better, people would say. He was also much more well-known at the time. Leibniz usually provided better notations. And kind of some of the words that we still use really come from Leibniz. He loved the dy dx notations. Okay, Newton really did like dots and things like that to represent his derivatives. So we use this dy dx notation a lot. And so one thing that we often do when we're doing the chain rule is apply that dy dx notation. So when you do the derivative of a composite function, we kind of think of the inside stuff being like a different function, a u. Okay, so when you do a dy dx, really you do a dy du times a du dx. Okay, so we kind of think of this as u to the 9th power. Okay, so we have something to a 9th power. All right, we've done that. The derivative of this something to the 9th power is 9 times our something to the 8th. Okay, but then you times by the derivative of your something. So 5 times 4 is 20x, and the 5 is gone. Last but not least, you can just replace the u back with what it was. The u was 4x to the 5th minus 5. And so we're back to where we began. Now, this notation is actually really, really useful as we progress through calculus. We use this u substitution idea, this idea that you can let this function be a different name, and we use that letter u. We use that a lot in what will be our module 5 on integration, the opposite of derivatives. And we use that idea of letting an inside thing be a u to help us with our notations and our calculations. So something that will come back to us does the same thing in the same ways, all right, but just a little bit more with that type of dy dx, dy du notation. Okay. All right, with that, that's all I've got for you on the chain rule. Again, how we do derivatives of composite functions. So when you have functions inside of functions. All right, good luck.